talk about free fall a little bit. We talked about in class what free fall was. So this is just a review of what it is. I would just want to do a couple examples, and we're going to do some practice problems so we feel a little bit more comfortable with this. So as a review, remember we watched those videos of the book falling and a bowling ball and a feather falling. We talked about a book falling. We watched a bowling ball and feather fall. And if we just drop them in the room, we would expect that the bowling ball would hit first, right? And we talked about that's because of air resistance. And that's kind of what we're used to. But we went to that NASA laboratory there, and they were able to go ahead and then suck all the air out of the room to take away all the air resistance. And when there is no air resistance, both the feather and the bowling ball landed at the same time. Okay, and that's what we talked about, is that all things will accelerate at the same rate. So that's a really important concept. All objects accelerate at the same rate. The little note there is that if we ignore air resistance, okay, so as long as we do, on Earth, they'll all accelerate at the same rate. That rate is very specific to where you are. So on Earth, it's always going to be about 9.8 meters per second squared. For all intents and purposes, in this class, we're going to just use 10 meters per second squared. So we call this value the g right here. This is an acceleration. And so we set g for this class equal to 10 meters per second squared here. So we're just going to be using 10. Now note that this is an acceleration. So that does mean that we should have a direction here, positive or negative, but we're just going to say it's down, right? So that's going to take care of our vector part of this right here. So we're going to say all things accelerate at 10 meters per second per second. What that means is its velocity is increasing at 10 meters per second. So no matter what time, I set this up kind of just to help us understand what's going on here. No matter where I am in this fall, my acceleration will always be equal to this 10 meters per second squared. So it doesn't matter if I'm at 0 seconds, this is 10, right? If I'm at my second here, this is also going to be 10, right? No matter what time interval I'm at, Earth is still pulling it down with the same force, and so it's still always going to be 10 meters per second. Now, the interesting thing is, if we go to the moon, the gravity there is slightly less. We're talking about 1/6 of the amount. If we go to Jupiter, I think it's about 2.5 times greater. So no matter what my time interval is here, that will always be, the acceleration is 10 meters per second squared here. So I can go ahead and just fill that in for each of these right here. Now, my velocity, this is what's changing. Remember, acceleration is a change in velocity over time. So that's saying I'm changing 10 meters per second. A lot of times we see this as 10 meters per second squared. I sometimes just like to leave it as meters per second because that's really telling me what's going on. It's increasing 10 meters per second down every second. So after 1 second, this would be 20. Oh, don't want that right there. This would be 20 meters per, sorry. This would be 10 meters per second after 1 second. I was jumping ahead there. So let's get rid of that one here. You know what? I think I just might use text boxes. That might be a little easier to fill this in here. So I'm going to just make a few of these real quick. There we go. So in this case, I'd be going 10, right? It increases 10 every second. So after 2 seconds, I'm at 10. I'm going to increase another 10. So I'd be going 20 meters per second. After 3 seconds, I increase another for 1 more second, right? From 2 to 3 seconds, it's 1 second. I increase another 10. And then from 3 to 4 seconds, it's 1 more second. So I'm going to increase another 10 because that's what I'm doing. I'm increasing 10 meters per second every second. So 30 plus 10, that's going to give me 40 meters per second here. And then I have finally 50 meters per second here. So notice here, it's just whatever my time is times this is going to be my velocity. So we can actually sum this up into an equation here of V is equal to acceleration times time. And in this case, my acceleration is going to be G. So in free fall, velocity is equal to my G equal to T. Now, there's one little caveat here, right? So this is my final velocity. This is assuming we're starting from rest. And if you're starting from rest, this is for sure always holds true. But if we're not starting from rest, we have to account for that initial velocity right here. And so that's going to be V initial. So what that means is if I'm starting at 20 meters per second, I'm still increasing at 10 meters per second. So if I start at 20, I'm going to go up to 30. So even though that's a 1 second increase, because I start at 20, it's still going to go up. So we can always find our final velocity by taking our initial velocity plus g times t. So this is one of the kinematic equations we're going to use for free fall here. Another thing we're going to look at right here is distance. So I can also find distance is equal to the average velocity times time, right? That's a basic equation. We've already used that before in kinematics here. We'll get rid of here. We'll create a new one. So this is equal to my average velocity. So I'm putting average right here times my time here. Sorry, this is a little messy. Okay, so what's my average velocity between 0 and 1? Well, I'm start at 0. I end at 10, my average between the two. So I add these two up. So that's 0 plus 10. My average velocity here is going to be 5, right? And I do that for 1 second. So 5 average velocity here for 1 second. Well, that's going to get me 5 meters here. So in the first second, I go from 0 meters to 5 meters. Okay. Well, then I'm going to go from 1 to 2 seconds here. Now I was started at 10 and I go to 20. So I add these two up. That's 30 divided by 2. My average speed here is going to be 15 meters per second. And I do that for 1 second. So I go between just this time interval, 15 meters, but I already went 5. So that's going to be 20 meters because I traveled 15 and I already went 5. Okay, well now I'm going to go ahead and look at the next second right here. Okay, my average speed would be 25, right? I'm just taking halfway in between these two, and I travel that for a total of 1 second, right? So that's going to be 25 plus 20. So I will then have gone 45 meters. All right, that kind of does that funny thing there. Okay, then from 30 to 40, the average is 35. So that's going to be 35 plus what I've previously already gone. So I'm going 35, and I've started at 45 meters. So 35 plus 45, that's going to give me 80 meters right here. All right, not the best. I should have probably just put more text in there. That's okay. And then the last one, the average of 40 to 50 is 45 for 1 second. So that's 45. So 45 plus 80, this is going to be 125 right here. So 1, 2, 5 meters right there. Now notice right here, there's kind of a pattern that goes on here. Okay, if I take this time and I square it, right? Well, that's just giving me 1 squared, and that gives me 5. So really, it's this squared times 5, right? Well, if I do this t squared, that's 2 squared. That gives me 4 times 5 gives me 20. 3 squared, that's 9 times 5. That gives me 45. So there's actually a nice equation for this. Distance, and we talked about this already. This is just a nice little review here, is equal to, if I start from rest, it will always be 1/2 times my time squared times g. Now I said just times 5, right? Well, notice here, this is 1/2 times g, right? That's 5, and then times my time squared. So we can use this equation for our distance. Now, as long as we're starting from rest, in these cases we use this equation right here. So now we have two equations. We're going to use this one right here and this one to solve our free fall problem. So we're going to go right down here to the ones we did together. We're going to work just some of these out. I went ahead and I put these equations right here. Okay, so this is my final velocity equals my initial velocity plus gravity times time. And then I have my distance. Now I had this part, I put v initial times t. That's if you start with it. But if v initial is there, then we have that equation we just have right here. So the thing we're going to want to do is identify what we have. Okay, so in all of these problems, we know that g is equal to 10 meters per second per second. Then it says, what will its velocity be after 6 seconds? So now it gives us time is equal to 6 seconds. And it wants to know what will its velocity be. So I'm looking for a final velocity. So it's asking for v final. So the only equation that has v final is this top one. So I'm going to go ahead and write that equation here. V final equals V initial plus G times T. It's starting from rest, unless it says otherwise. We're always going to assume it's starting from rest. So I'm going to go just 0 here, plus, and then gravity times time. So that's 10 times 6. I'm going to leave off my units, and I'm just going to come back and put them here. So that's my gravity is always 10. My time is 6. So this would be 60. And then I'm putting back my units here, meters per second. Now that should make sense, right? Because I stopped at 5 seconds right here. If I took it one more, this should just increase by another 10. So we get, and mathematically now we see that pattern kind of working out here. So let's go ahead and do a couple more of these. 2, an object falls from a high building and hits the ground 9 seconds. Ignoring air resistance, what is the distance that it fell? So again, write down what we know. We always know that G is equal to 10 meters per second per second. Now it gives us that time is equal to 9 seconds. What is the distance that it fell? Well, before I had G and T and I found the final velocity, but now I have G and T and I want to know the distance. So I'm going to use this equation right here. An object falls from a high building. Again, we're going to assume that the initial velocity is 0. Unless otherwise stated, always assume the initial velocity is 0 for this, our class here. So I'm going to go ahead and now put distance, and it's just equal to 1/2 GT squared. And I'm just going to go ahead and plug one in I have, right? So I have 1/2 times 10. That gives me my 5 right there. And then times my time squared. So this is 9 squared. So that's going to go ahead, and I'm going to do half of 10, the first part, that's 5. And then 9 times 9 is 81. And then I'm going to take 5 times 81. Well, I know 5 times 8 is 40. So I took off a 0, put it back on. That's going to be 400. And then 5 times 1 is 5. So 405 here. 405 meters right there. All right. So again, identify what we have. Look at the equations. We're looking for distance. So this is the only equation with distance. This is the only equation with V final, right? They both have gravity and time. So we just need to identify which one we're looking for here. All right, I can actually I'm going to drag my equations down here just so I can keep those references here. Okay, so during a tornado in 2008, the Peachtree Plaza Westin Hotel in downtown Atlanta suffered damage. It's one of the tallest buildings here in the United States. Suppose this piece of glass dropped near the top of the hotel 250 meters. Okay, so first, this gave us a distance, 215 meters. If you're ever struggling of what to know, remember, we can identify by the units. Distance will always be in meters. Velocity is in meters per second. Time is in seconds. Okay, so by looking at one of those three, and acceleration is meters per second squared. So by looking at those, we can identify what it is right. This is meters, so I know it's a distance. Okay, so it gives me this one right here. Also, I know that G is equal to 10, right? We always have that. As long as we're on Earth, we have that going for us right here. So now it's saying, okay, you have these two. How long would it take? Well, I have distance, I have gravity, and I'm looking for a time. So I'm going to use my distance equation, write this last one right here because we're, again, assuming V initial is 0. And I have G and I have D. So now I can go ahead and solve for T. So let's go ahead and throw one more box in here. So distance is equal to 1/2 GT squared. So I'm going to go ahead and plug in what I have here. So 215 is equal to 1/2 times 10 times T squared. Okay, so that's going to be 215 divided by 5, right? So if I get here, I get 5 on this side. So well, let me go ahead and just write here, 5T squared. I'll skip a step. So now I divide both sides by 5, right? So I get T squared on its own. So if I divide 215 by 5, I know that 200 divided by 5, 20 divided by 5 is 4, so 200 is 40. 15 divided by 5 is 3, so that should give me 43 here is equal to T squared. And then I want to go ahead and take the square root of both sides. So on your calculator, you're going to have to either hit square root and then 43 enter, or hit 43 square root enter, depending on what you're using. If you do have a phone, you can always turn your phone sideways to go ahead and get this answer. I know that it should be somewhere between 36, right? Because 6, because 36 and then 49 is 7. So it should be somewhere between 6 and 7 here. I guess this is about 6.6 maybe. I'm going to go ahead and grab my calculator here just to double check this. So I'm going to put this into mine 43. And I get, yeah, we're going to round up, just say 6.6 right here. So T is equal to 6.6. And we leave units off here, but we cannot forget units down there. So I went ahead and put my units right there. Okay. So the second part of this, ignoring errors, is what will the velocity be? Well, my givens are still the same, right? I still have distance is 215, G is 10. So I can go ahead and write it again. So 10 meters per second. I did find out, though, that my time is 6.6 seconds. So if I'm looking at my equations right here, my final velocity, and again, I'm assuming V final equals V initial plus gravity times time. I'm assuming that it starts from rest, so V final will just then be 0 plus 10 times 6.6 seconds. So my velocity should just be 66 meters per second here. Okay. So not pretty straightforward in this part. We can use this time for this one right here, and that makes our life a little bit easier. All right, question 4 here. An object falls from the Transco Tower in Houston and takes 15 seconds to reach the ground. What is the velocity at impact if the error is ignored? Okay, so it takes 15 seconds. So what do I know? I know that, again, G is equal to 10. You always start with that. I also know that it takes 15 seconds. Okay, now that's all it gives me right here. This is 15. I know G. So I'm looking at my equations here. I can pull those down or maybe leave them right here for now. And I'm looking for distance. So distance is equal to 1/2 GT squared. So distance is equal to 1/2 GT squared. I can go ahead and plug these in, right? So I know G and I know time. So that's equal to 1/2 times 10 times 15 squared. So I'm going to go ahead. I can do this out. I know half of 10 is 5. So 5 times 15 squared. Remember our perfect square roots here. 15 squared is, I believe, 225, right? Yeah. So 5 times 225. Well, I know that 5 times 200 would be 1,000. 5 times 25 would be 125. So I should get 1,125 meters right here. Okay, so this one is nice. So we didn't have to do any square roots. We just had to square it right here. So you got to feel comfortable in your calculator going between the two. Okay. Oh, you know what? I reversed this. I did how tall is the building. I just did that part right here. This one's the velocity and the impact. Okay, well, let me just shift this down. Yeah, I actually can do this straight out from the information it gives me. And so, what is the velocity impact? Okay, I skipped ahead. Let's go back, though. The initial GT. All right. So I'm going to go ahead and plug this in, right? The V initial we assume is 0. And then gravity is just 10 times and then 15 seconds. So what is the 10 times 15? 150 meters per second here. Very straightforward. All right. What is the acceleration at the second? Okay, this is the part. Don't get confused here. Don't mix it up with velocity. Acceleration, if we're roughly at about the surface of the Earth here, is always going to be the same. So notice here, my table, acceleration is always the same. It's not changing. So when you do this, I should expect this acceleration to be at 10 meters per second. The fifth second, same thing, 10 meters per second. All right, let's do one more together here. This is part of the homework. There's a little more, but I'm going to just want to work this, and hopefully you can start catch on and feel more comfortable with it. If the Transco Tower were actually 3,000 meters tall, how long would it take an object to free fall off the building, ignoring air resistance? So in this case, my distance is equal to 3,000 meters. Okay, my gravity is still 10 meters per second. Okay, and then I just want to solve for time. If I'm dropping it right, the initial is 0. So I'm just going to get looking at my equations right here. I can pull those down. Distance equals 1/2 GT squared. So I'm coming here 1/2 GT squared here. Okay, so I'm going to go ahead and plug these in. The distance is 3,000 meters. And then 1/2 of 10 times t squared. So that's 3,000 equals 5t squared. Divide both sides by 5. Well, I know that 30 divided by 5 is 6, right? And I cut off 2 zeros, so add them back up. 600 t squared. All right, and when I look at this, I immediately think 625, right? So that's 25 squared. So this should be a little less than 25, maybe 24 and a half, something like that. So let's go ahead and plug this in our calculator. 600 squared, 20, yeah, about 24.5. E equals 24.5 seconds. All right, so notice here with this same process going out through all these. So hopefully you feel a little more comfortable. The key is identify what we know. We have these two main equations right here. I'm going, this box right here is what I'm talking about. This first one is the first equation we did. The final velocity is always just going to be equal to gravity times time plus any initial velocity that you might have. Okay, as long as it starts from rest, it's just going to be gravity times time. We saw that right here, right? So if it's 6.6 seconds, 66 miles per hour. 15 seconds, 150 miles per hour. Or sorry, not miles per hour, meters per second. The other equation we use, as long as it starts from s, we're just using this one right here. So distance equals 1/2 gt squared. Now that 1/2 g, if this g is always 10, that's just going to be 5t squared. Okay, but as you see, going on the rest of this, there is a problem here on the moon where you do that. And then we can solve for either the distance or the time in these cases to kind of get that answer. So hopefully you feel a little more comfortable with this as we do these free fall practice problems.